What's the point of having developed a science good enough to make predictions if all you're going to do is sit around and wait for them to come true? I spend all my time looking at climate changes. We've increased carbon dioxide levels by about 40% over the last 150 years.
We cannot continue this way.
Viruses and pests and pathogens and insects are growing like twice as fast as they used to grow because they're no longer getting cold during the winter.
That could take out entire agricultures. This is like people dying.
All of this with the global warming and that, and a lot of it's a hoax. It's a hoax.
Trump is kind of NASA's boss. Do you ever worry about waking up in the morning and getting sacked?
We need to be adapting right now to make us more resilient to the climate that we have and the climate that we can predict. You can make a difference. Anything that's happening that matters is being done by individuals who are finding ways to magnify their voices and to amplify their concerns.
This week on the show, we have Gavin Schmidt, who is the director of the NASA Goddard Institute for Space Studies, and he works on global warming. And he believes we must get off our carbon diet. And while, yes, the climate has fluctuated from the Ice Age till today, he believes that as humans, by burning fossil fuels, we are actually making the climate much, much warmer than it should be, and we're going to pay the price when it comes to sea levels, when it comes to resources, when it comes to actually people dying. The weird part is that his boss, President Donald Trump, doesn't think the same way. And so he's in this weird situation where the executive branch is trying to open up the more burning of fossil fuels. And of course, Gavin knows it's actually going to kill us. So whether you're a fan of global warming, a believer that we're causing it or not, you must watch this show just to understand the science behind it. And that's really what this is about. Science and modeling and basically predicting what we're doing. So there you go, that's what's happening here. And inside London Real Academy, we are doing something special because we are announcing the opening of our Speak to Inspire 6-week accountability course. I'm gonna walk you through as your personal mentor for the next 6 weeks and show you how to speak with persuasion and influence, just like all of the great guests on London Real. I'm gonna show you how I crafted and delivered a TED Talk that was watched by over 275,000 people. I'm going to show you how to be a storyteller, how to use body language, how to meet the crowd before you give a talk so you can do the absolute very best. And this is not just if you want to be a great public speaker, it works in the boardroom with clients, or if you just want to be the one that can tell a great story at a party. There'll be a limited number of people. This is going to be our most wanted course ever. So get in on it now. There's a link below and join me for Speak to Inspire. We won't do this again until next year. It's going to be absolutely amazing. And now I leave you with Gavin Schmidt of NASA. This is London Real. I am Brian Rose. My guest today is Professor Gavin Schmidt, director of the NASA Goddard Institute for Space Studies. one of the world's top climate research organizations. You're only the third person to hold this post for NASA, taking the role after James Hansen, the father of climate change awareness. You've written over 120 publications that specialize in simulations of the past, present, and future, and Scientific American cited you as one of the 50 research leaders of 2004. You propose that climate models are skillful, but more importantly, it's essential that we get off our carbon diet. Gavin, welcome to London Real.
Thank you very much.
It's great having you here, but this isn't your first time in London, is it? You spent time here, you're born in this country.
I was born in London, born in Barnet, and lived in Hammersmith for a long time.
What's it like to come back and see this city? It's kind of rebirth, or seeing it grown up. Is it weird being here?
London has always been these multiple layers on top of each other, kind of cheek by jowl, and the Victorian pub next to the Roman wall, next to the brand new building, and the 30 years it's been since I've lived here, you've just seen more layers being added on top of that. Plus, I think it's become a lot more friendly for pedestrians, for cyclists. There's less traffic in the centre, there's a lot more open space in pedestrianised areas. I have to say, I'm liking it. I love the bike system.
Okay. And you've been in New York City for the last 20 years.
Yeah, well, a lot of the same things have been happening there too. Things have been cleaned up. There's a lot of great new development. There's been a lot of pedestrianisation. There's been a lot of support for cycle infrastructure. And that makes, I think, both of these cities much more livable than they used to be.
How do you compare those two? I mean, is it the tale of two cities now as we go into the future, or are they very, very different in your eyes? Because they kind of do compete.
Yeah, the reason why I stay in New York and that I live in New York is that the people there, it attracts people from all over the world, and you meet people, and there's no default about what it is you're supposed to be, or how you're supposed to talk, or how you're supposed to live, and people are basically taken for who they are for the most part. It's not a perfect city for obvious reasons. And that was always very refreshing to me. Growing up in the UK, traveling around, living in Europe a little bit, I often felt that you had to always be kind of defensive about the fact that you had a German last name, or that you spoke foreign languages, or that you ate funny food, or that you had cousins that lived abroad, or that you were Jewish, or you were this, or you were that. And it's not that any of those things are problems, or that people were mean about it or anything, but it was just like this constant, always being on the defensive. And in New York, that never happens.
Right, because you're in a melting pot full of weirdos.
Where everybody has a story, and if you're not interested, fine, you move on, but there's no default.
Yeah, I would argue that London today, it's probably pretty diverse when you
there's no
cruise
question
around.
that it's more diverse than it used to be, and so I like coming to visit here, so don't misunderstand that. I enjoy spending time here.
So much to talk about. I don't really know where to jump in, but first I want to say something I realized after watching your TED Talk when you dropped the Fortran reference, which is a computer code that they used to teach back in the 60s, 70s, 80s, which I think they're still using in climate science. Not that it doesn't work.
No, it works really well. That's why we keep using it.
But I used to code Fortran when I was a kid, and I learned when I was about 8th or 9th grade, and I actually ended up working for the Scripps Institute of Oceanography when I was 16, helping one of the scientists there with kind of climate models, and I was programming these silicon graphics machines, which were like one of the very first really beautiful 3D graphics pieces of hardware that you could really kind of watch climate models over years and years. And we were using data from buoys that were spread across the Atlantic and Pacific Ocean, and El Nino was the big thing.
Right.
And climate change wasn't really something that the public was talking about that I remember. El Nino would come along every now and then and kind of knock some industries out and shake some things up. Right. But I forgot that I was kind of involved in some early days here. Now it's progressed a lot, but I was in this kind of science and institute place where they would run a lot of simulations and then try to figure out what was going on. Do you remember those days? And how can you fast forward us to today?
Right.
Has it gotten a lot bigger? Has it gotten more political? Has it gotten more public, your work?
So all of those things, right? So I remember using those same SGI machines when I was doing my PhD here at UCL. And you know, I remember the first time somebody said, "Hey, download this browser thing," and I remember like the first thing we looked up, and there was a list, and we looked up somebody in Argentina who had a site on how to dance the tango, and we're going, "Oh, this is cool. I wonder if it will amount to anything."
It was the early web,
it was
like 91
it was like,
or something.
Yeah, Mozilla, right? It was maybe 93.
Okay.
But, oh no, it could have been 91. Yeah, that was when I was there. Anyway, so you know, me too. I started off doing coding, small scale things, ocean modeling as well, and you know, my PhD was of interest to perhaps 4 people around the world, right? Which
like every great PhD.
You know, which wasn't perhaps the smartest career move that I made. But it was after that I got a job, and they said, well, you know, you could do that kind of theoretical stuff, but really we're moving into this climate business. And I said, oh, that's interesting. They said, oh yeah, we're gonna be looking at the ocean circulation and the thermohaline circulation in the North Atlantic. And I said, oh, that sounds fantastic. And I remember putting the phone down and then turning to my advisor and saying, what's the thermohaline circulation?
But you were interested.
I was kind of like, you know, blagging just to get a job, but it became this really big thing. And so I went into this really as somebody with skills in coding, in the theory and things, but really without much experience or understanding of the climate issue as a whole. And so I went to Montreal and I spent 3 years just kind of basically soaking up everything that there was to be soaked up in climate. And this institute, they'd only just started, and so they were doing the same thing. They were bringing in all these people from all over, tell us about everything. And it was a great fertile period. I like to kind of, you know, so I did some courses, I read some books, and you know, and then started working on models of the climate that were kind of relatively simple. I mean, complicated, but relatively simple. And I ended up suffering from what was called dimension envy, right? Where you know you don't want to just be looking at a 2-dimensional view of the whole world. You know, you want to see everything, 3-dimensional, 4-dimensional. And so I then moved to New York, where I got the opportunity to work on really complex models that had all the dimensions that you could possibly look for, where you're not thinking so much about, you know, how beautiful your theory is, but you're thinking much more about how accurate this is, how realistic are the simulations, and you're trying to understand the simulations for things that happened, you know, hundreds of millions of years in the past, out to, you know, thousands of years in the future, and everything in between. And when you start to deal with the complexity of the real world, as opposed to the kind of nice, neat theory that you know, students kind of grow up with, what you find is that it's not just 4 people that care about what you do. It's 40 people, then it's 400 people, then it's 4,000 people, then it's 4 million people, then it's pretty much everybody cares about the problems that you're dealing with. And then that kind of pushes you to be thinking, well, hold on, like we're doing something that now matters. It's not just an academic issue. It's something that matters. So we have to do a better job. We have to make it more realistic. We have to see, okay, what are the questions that are coming from outside that we need to answer? And you kind of rejig the science a little bit to answer questions that are coming both from the public or from policymakers or from decision makers or from, you know, or from the media. And you think, okay, well, we can answer those questions because you've built these tools that are so multifaceted that you can use them to answer an innumerable number of questions. And it's not just, well, what's the global mean temperature going to be, or is it greenhouse gases that's caused the warming? It is, but that's not a very interesting question after a while.
In your TED Talk, you talk about this concept of 14 orders of magnitude.
Right.
So going down from a very tiny amount of measurement of, what, 10 to the minus 6 meters, or maybe less.
So that's the size of a nucleating particle for a cloud droplet.
Okay.
Right. So that's what causes clouds. It's happening right at the micro scale.
Okay.
And yet clouds have such a massive impact on the climate that they're affecting the whole global climate, which is like 10 to the 8 meters.
Right.
So you've got these like 10 to the minus 6, 10 to the 8. It's like 14 orders of magnitude. It's massive. There's no single theory, even in theoretical physics, that works across such large orders of magnitude and is still correct.
And
right?
for people that know, an order of magnitude is kind of a 10x
Right.
step between each one.
Yeah,
So,
I mean, like powers of 10.
Yeah,
There was a classic
10 to the 14th power.
Right. So
Of
10
size differences.
one with like
Yeah.
14 zeros, and you need to get that one right, and you need to get that one right at the end right as well.
And then on the other axis is your time orders of magnitude.
Right.
So very micro pieces of time out to just long millenniums.
It's the same thing, yeah. So you're doing things that are happening on the microsecond scale, millisecond scale. You know, the sun comes out from behind a cloud, warms up the ground, there's evaporation. All of these things are happening very, very quickly. And yet the processes that control climate, you know, have timescales of thousands of years. You know, what's going on in the ocean, you know, there's water in the Pacific that's 10,000 years old since it last saw the air. Right? And so circulation works on a very, very slow timescale, but you've got to get the really fast things and the really slow things, and that really that's a real challenge computationally. And so what's been happening over the last few decades is that every 10 years we've been able to get another like order of magnitude of stuff in
that you feel like you can model
that you feel that you've got a real grip on.
Okay.
And
every 10 years in order of magnitude.
Right.
Yeah, that's still slow. I mean, it's amazing that you can accomplish that. But
right. I mean, it's actually massive, and you go, "Oh my God, this is so impressive." But you know, the problem is that if you want to be able to predict what's going to happen in 2100 with perfect accuracy, because you've understood every single process all the way down to the millisecond micron level, you basically are going to have to wait to 2100 to work that out.
Right.
And that's not acceptable.
In your TED Talk, there's some beautiful graphics in there, and you kind of show, okay, this is our, you know, what we can do as far as modeling the world, and here's what it starts looking like, and then this is the world, and you can see a lot of things happening. You're like, there's some cyclones coming up. We didn't model those, and how could we? And then it could be the pollution in China. It could be this thing here. It could be this thing here. All these little variables that are almost impossible to model, and
So what you're doing is you're trying to model the processes, right? So these models are very different to what you might be thinking of as models. And so, you know, somebody has done a little bit of statistics. They think of a model as like, you know, a line through the points, right? Okay, well, that's not what we're doing. Or you think of a model like, I don't know, if you're in biology, you think of a nematode as a model for, I don't know, human genes or something like that. Okay, We're not thinking like that. What we're talking about is trying to put together all of the different processes that we see happening in the real world. So you go to the Arctic, right? You know, you've got the sun that comes down, it reflects off the ice melts, and then the sun goes into the ocean. Those things can be encapsulated, they can be measured. You can work out how reflective the ice is, you can work out how quickly it melts, how fast it forms. And then you put all of that into code, and then you join it up with all of the other bits and pieces of the system. Right, so the clouds, the winds, the ocean circulation, the rivers, the soils, the lakes, all of it. And you put each of them in, and then you just kind of basically say, okay, well, the winds did this, and then now what's the ocean going to do, and now what's the ice going to do, and now what's the ocean going to do, and now what's going to, and you just keep going around and around. Right. And all of the things that you mentioned that you can see in those animations, the tropical cyclones, the storm systems, the pollution coming up and swirling away and dissipating.
The vegetation that's absorbing sun and water vapor
and growing and being fertilized by carbon dioxide and being desiccated by drought and all of those things. You can put all of that together, and what you see are these emergent patterns, right? These things that we didn't code in specifically, but they just kind of emerge when all of those things are working together. There's a great example of what that is. Have you ever watched like a big flock of birds, right?
Yeah.
So a big flock of birds, and you look at them, and they're swooping and they're gyrating, and you think, oh my God, what a beautiful pattern that they've designed. But they haven't designed any pattern, right? That's just an emergent property from each of the individual birds. All they're doing is paying attention to what the other birds around them are doing. Right, so if the bird on their left goes a little bit that way, they go a little bit that way, and they don't do it perfectly. So it's not totally. So it's a little bit random. It's a little bit chaotic, but the beautiful swooping patterns, they didn't design it. It kind of just came from those small-scale interactions. Okay. So the climate is exactly like that. The patterns that you see, they emerge from these small interactions. The solar radiation over a day, the wind pattern, the clouds, all of these things, and the rotation of the Earth, right? All of those things fit together to create a storm, to create a tropical cyclone, to create the seasons.
Okay, that sounds massively complicated. And also, if you forgot something like the vegetation, that could throw the model off completely.
Well, so you don't forget about these things.
Okay.
But earlier on, you didn't include all of the variances. So you'd say, okay, well, let's just keep the vegetation fixed. Let's just assume that the vegetation is always the same, and it doesn't vary from one year to another, which is not a terrible approximation. And then as we get better and as we get more experienced and as we get bigger computers, we start to say, okay, well, let's loosen that approximation. What if it changes a little bit as a function of drought, as a function of rain, as a function of carbon dioxide, and then you start to see slightly better fits to the observations, and you can use more interesting information to check how well the models are doing. But every time we've done that, it doesn't change the big picture. The big picture has been pretty stable.
And the big picture is what? Is that we have to get off our carbon diet, which is not always what people want to hear.
Right. So the big picture. Before we go into what we should do, what's the big picture for what is, right? So what's actually happened over the last 100 years or so? So we have seen global warming. It's been about 1 degree Celsius. Nobody really knows what that means, but it's about a quarter of the difference between the pre-industrial period and the last ice age.
Okay.
Right? So it's not a trivial amount of things. So, it's
and that's
it's
what
a
period
deal.
of time?
Over the last 100 years.
100 years, okay. It's gone up a quarter.
About a quarter of an ice age unit. How about that?
A quarter of an ice age unit.
Yes.
Okay, all right.
So if an ice age unit is like how cold it was in the ice age compared to now, so the ice age was about 20,000 years ago.
Yeah.
It was about 4 or 5 degrees colder than pre-industrial. So with just about 1 degree, it's about a quarter of that.
Okay.
So, that's a better context.
Yeah, all right.
The planet has warmed, right? We see it in everything. We see it in the weather station data, we see it in the ocean data, we see it in the retreat of the glaciers, we see it in the movement of ecosystems up the mountains towards the poles. We're seeing it in growing seasons. We're seeing it in 1,000 different parameters, right? There's no question about that. Why is that happening, right? There's a ton of things that cause climate to change. Right? We have the whole of geological history to see how many different things have caused the climate to change. We've had asteroids, we've had massive volcanic eruptions, we've had continents moving around and changing the ocean currents. But none of those things have really happened in the last 100 years. The last 100 years, we've had the sun has been doing a little bit. The volcanoes have gone off. Krakatoa went off, and Pinatubo went off in '91. Mount Agung went off in 1963, cooled the climate by about 0.2 of a degree, and maybe just about to go off again. I didn't check the news this morning, but it's been rumbling all week, and people have been evacuated from the same volcano. That affects the climate. But then there's all these things that we've done, right? So all the human input. So we've chopped down a lot of trees. Really, a massive amount of trees. We've increased the amount of ozone pollution at the surface, smog, and we've decreased the amount of ozone in the stratosphere because of our use of spray cans back in the day.
What was that compound? It wasn't
CFCs.
CFCs.
Yeah.
Chlorofluorocarbons.
Chlorofluorocarbons.
Which we no longer emit. We were good about that?
Yeah, so we've actually stopped emitting those completely thanks to the Montreal Protocol. Yeah. And they're decaying slowly because they're very long-lived. That was part of the problem. And they're decaying slowly in the stratosphere. So we're just starting to see the ozone recovering and the ozone hole recovering from the peak harm that we did it to it. So we did that, and we've emitted a lot of greenhouse gases. Right. So the biggest one is carbon dioxide. Second biggest is methane.
Right.
Nitrous oxide comes from agricultural activity for the most part. Methane comes from mining, from agriculture, from cow farts and the like.
There's that
always
famous
funny
documentary Cowspiracy, which just points to methane and says per unit it's much more destructive than carbon dioxide.
Yeah, but some of the numbers in that documentary are not valid. So they over-egg their pudding, so to say.
Okay, they exaggerated some statistics.
So some of the stuff in there is exaggerated.
Okay.
But methane is a big deal. But carbon dioxide is the biggest deal.
Okay.
Right? And so that comes from burning fossil fuel, burning oil, burning coal, burning natural gas. and anywhere that you get those things from. So shale oil, shale gas, tar sands, all of those things. It's the same. It's the same basic idea. And we've increased carbon dioxide levels by about 40% over the last 150 years. And that's the dominant thing. And when you do each of those things in turn, and you see, okay, well, what have the natural things done? And the basic answer is that over the last 100 years, natural things wouldn't have changed the climate at all. Yeah, there have been a few blips there and there, but we'd be basically the same as we were 100 years ago.
Even with volcanoes?
Even with the volcanoes.
Okay. That's what your modeling's taught you, or that's what?
Well, so that has to be a model, right? So what you're doing there is a counterfactual, right? Because it didn't just happen that only natural things happened, right? We only had, in the real world, there was only one path that had us and all the natural things all together.
Right.
So when you're trying to do an attribution study, when you're trying to say, well, what caused what you need to do is you need to take out, factor A, take out factor B, take out factor C, and then put them all together again and see if you can explain what's going on. And when you can explain it, which one of those factors is the dominant thing.
Right.
So that's what you do. So you need to have a model to do that.
Right. So say, for example, the last 100 years, we have data, so we know what happened.
Right.
Now say you could go back 300 years and 400 or 500 years and predict each increment of 100 years correctly. You would hope or assume your model might predict that last 100 years correctly, and you compare that with the real data. Is it something like that?
It's not quite like that.
Okay.
The hindcasts we do, they're not predictions as if we were living in 1900. They are, you run the models forward, knowing when the volcanoes went off, knowing what the sun was doing, knowing how much extra greenhouse gas was in the air, because we know those things, right? So we put those in, and then you say, okay, well, how much warmer does it get when you just have the sun going on? Well, how much warmer does it get when you just have the volcanoes? Well, it actually gets a little bit colder. How much warmer does it get when you just have air pollution or ozone or... Anyway, you do all of those things, and what you basically find is that the only thing that warms like we've seen, that explains what we've seen, is the effect of greenhouse gases.
Okay.
So let me use another analogy that might be useful. So you might have talked about like the Higgs boson and the Large Hadron Collider at some point.
Yeah.
Fascinating project, right? So you've got an enormous amount of data that's being produced by these massive collisions all the time, and then they look for anomalies, right? So they have a model for what it should look like if everything is as they expect, and then they try and find anomalies. But you see anomalies all the time because things are random and you get departures. And so if they see a 2 sigma anomaly, they say, nah, that's not enough, right? Like that happens too often.
Yeah.
3 sigma anomaly, they start to get interested. 4 sigma, they're going, 5 sigma anomaly, that's when they say, okay, if we're seeing a 5 sigma anomaly, then we're seeing something that needs to be explained. And we're going to try and explain it with our theory of the Higgs boson, right? We're doing the same thing, right? So we have a theory, a background theory for how things are working when you just have natural things going on, and where we are, the signal in the temperature that we can go and measure, that's a 5 sigma anomaly from what we expect.
Okay.
Right? So it's the same level of detectability that the Large Hadron Collider people had for the Higgs boson.
Which everyone says must be correct, and that they've found these new particles, and yet you have people that disagree with you.
Yes.
And if the science is so obvious to you and the people that you work with, why is it so controversial?
Well, the science is controversial not because of the science, right? So as sciences go, nobody is being hounded out of the field because they're frauds or because they faked a graph in a paper, which happens all the time in biology or in microbiology or anything. We don't have those kinds of skills. We have those kinds of standards. We haven't got those kind of scandals. But people attack the science because of what it implies, right? And we're not the only science for which that is true. Evolution in some parts of the world, the southern US or in Turkey, is attacked because of what it purports to say about man's relationship with God. Now, I don't think it has anything much to say about that, but opinions differ, as they say. And so the way that people deal with difficult science is to react by shooting the messenger, because it's much easier to do that. Oh my gosh, this scientist is an imperfect human being, therefore I shall ignore their science, because I don't really want to pay attention. I don't want to conclude that humans are impacting the climate.
Because it's not in my economic interest.
It could be economic, it could be worldview, it could be religious, it could be ideological. I mean, it could be tribal, right? You know, science comes from, you know, highly educated people on the coasts of the US. I mean, that's a horrible stereotype. I mean, science is being done all the way across the US, but you know, it's clear that there are cultural divisions in the US that are being, you know, this is a period in which they're amplified, and unfortunately, climate change and climate science has been taken along for that ride, and so that's a pretty bumpy ride. But you find people who have never given climate science a thought dismissing the science of climate, mainly because that's what their tribe is doing. And there's a few key voices that are trying to break out of that, but unfortunately that's a big part of it.
And your critics say climate's always changed. You've heard this argument all the time.
But it's not an argument. Nobody disagrees with that. Climate has always changed. The issue is not, we thought that, like these idiot scientists who think that the climate didn't change before humans came around. No, I spend all my time looking at climate changes in the past. Like this last week, I was at a workshop looking at these massive warming events that happened in the Paleocene or in the Cretaceous or in the Jurassic. I mean, these are massive, massive changes, mass extinctions, you know, huge rearrangements of the climate system. Science is not unaware that big things have happened before. I mentioned the ice ages before. Like, it's not like, of course climate has always changed. That's a stupid question. Yeah. Right? It's not a stupid question.
But it's used a lot,
it's
right?
True.
Yeah.
But it doesn't imply what people are trying to make it imply.
Okay. Right? Other critics say it's not man-made. They say, well, all of this stuff, we can't attribute it to be that, right? You've heard that one as well.
Well, but then you show them the attribution studies and you show them how to do it, and you show them, okay, well, here's like 5 different ways to do it, and you all come up with the same answer, right? You know, they're just like, well, I'm just going to go into another argument there. You're a bad person. It's like,
you get that a lot.
I do get that a lot, and it's quite funny. I mean, you may resonate with this one, but you know, I haven't got a lot of hair, right? And I haven't had a lot of hair for a long time, and I kind of liken most of the personal attacks that come my way to somebody coming up to me in the playground at school and saying, "You dirty hippie, you should get your hair cut," and you're going, "What?" And so most of it is like, it's just like they insult you, but they don't know you. They have no idea who you are, what you do, or what things. And so you've got this like weird kind of internet doppelganger that exists, that people like they take their name and they say all these terrible things about that person, and it just happens to be your name and it's your job, but it's not you. And these people are just it's you know, you become kind of, I wouldn't say iconic, perhaps symbolic of other things that they don't like, or they can't. So
the intellectual arguments against your theories in science are just very base, and they don't have a lot of intelligence to them.
Because if you actually talk to the scientists and you go to the meetings and you see who's working on interesting things, the number of credible challenges to the mainstream view of what's been going on is pretty close to zero.
Okay, even though it's getting more momentum now, this thought.
Well, it's always been bubbling there, you know, and it bubbles up when it's useful for people to have it bubble up. Right. And so these things get amplified by commentators, these things get amplified by politicians when it's kind of useful for them to be doing so. And, you know, you'd rather wish that they didn't do that, they'd find something else to talk about. But, you know, there's a number of people here and a number of outlets in the UK and in the US that, that persist in total kind of ostrich head in the sand type of discussions on science.
Okay, which is kind of what's happening now.
Right.
Well, we've seen that happen, and so yeah, I mean, it's no surprise, or it's not new news that Trump organization is talking about that. It's very friendly to oil and gas and shale, and people think it's kind of reversing a lot of the policies that Obama had in place. And so the world's dealing with that, removal of the Paris Accord, and of course, Trump is kind of NASA's boss too, which I'm sure puts you in a difficult situation.
Right. So NASA is a pretty robust institution. It's a science institution. It's a science agency. It's not a policy agency. So the science that we do, serves an enormous range of end users, from people making weather forecasts to people tracking disaster relief, to people looking at long-term changes in ecosystems. The science that NASA does transcends a lot of the bickering that occurs just because of the climate change part of it. So
okay.
NASA is a $20 billion agency. Earth Science is about $2 billion of that. And the vast majority of that goes to support the satellite program that we have in low Earth orbit. So we have satellites up there measuring ozone levels and temperatures and sea surface spray and salinity and land cover change and clouds and the depth of clouds and the concentrations of clouds. We spend a lot of time looking at clouds. What else?
So that's why NASA is doing this climate research, because of the low Earth satellites. That's kind of why this agency does it.
Right.
Because on the surface, if I say National Aeronautical and Space, why are they doing climate change? That's why, right?
Right. So we're really the only agency. I mean, ESA is getting up there, but we're the only agency that for the last 30 years has regularly maintained monitoring instruments in low Earth orbit that have tracked the climate through all those El Nino events, through those big volcanic eruptions, and the data that's coming from those has helped improve weather forecasts, so much so that a 7-day forecast now is as good as the 3-day forecast was like even 15 years ago. And really, I mean, that's an enormous benefit to everybody. So the climate change part of NASA comes because we've been doing it for a long time, and now we've got trends, right? So a lot of these things were not put in space to look at how things were changing, but they've been in space long enough, and we have records that are solid enough that we can now see the changes. We can see the changes in temperatures in the atmosphere, temperatures in the stratosphere. We can see the changes in the gravity, the shape of the gravity field on Earth. Right, this is like incredible technology. So we have 2 satellites that are flying called the GRACE satellites, and they have a laser beam that goes between them, right? And what it measures is exactly how far apart they are, right? And you think, okay, well, what can you do with that? So as they're going around, right? If they go over a mountain, right, the mountain is a lot more mass, right? So the gravity is a little bit larger as you're just going over a mountain. So when the gravity is a little bit larger, it pulls the satellites together a little bit more. Not by very much, right? By like, kind of femtoseconds, right? But we can detect that. And so we can detect when it goes over a mountain, they get a little bit closer together. And when they go over the ocean, they get a little bit further apart. And we can track that. And so the idea with that satellite was to measure what the gravity field was, right? Because that's really important for the other satellites, so that we know exactly what orbit they're in, right? Because if you go over a little bit more mass, it slows down, less mass, it speeds up, right? So you need to know that very accurately. But those satellites have been in orbit since 2003. And not only have they mapped the gravity field, they've mapped the changes in the gravity field. And you think, okay, well, where's gravity changing? What does that mean? Gravity's changing? Okay, gravity's changing on the ice sheets because the ice is melting and falling into the ocean. And so there's less mass on Greenland. And so they used to slow down some, and now they're not slowing down quite as much. And so we can detect that trend even on a decadal scale. Okay. Right? So we can detect that we're losing ice in Greenland. We can detect that we're losing ice from the Alaskan ranges, and in fact all of the mountain ranges. We can detect that the ocean is gaining mass. We can detect the places where we're unsustainably taking out groundwater, right? The Californian Central Valley, northern India, China. There's less gravity there than there used to be. I mean, not that people are kind of bouncing like they're on the moon or anything, but there's less gravity there because all the water that used to be in the ground is now in the ocean. And we can keep track of those things, not because that's really what we wanted to do at the beginning, though, I mean, people did think that might happen. But, these things had design lives for like 3 years, and yet they've lasted 14.
Okay.
And so you get these trends. And so that information, the information that NASA is producing that is demonstrating that climate is changing, right? That's why NASA cares. It's like, well, explain this. Like, so do the simulations, do the data analyses, find ways to pull that information in and make it comprehensible, make it coherent with everything else.
Okay. If it wasn't for NASA, would we be way behind when it comes to understanding climate change, or?
I think so. I mean, NASA has been a huge pioneer. It hasn't done every single new thing. I mean, ESA has been doing some.
ESA stands for?
The European Space Agency.
Okay. Yeah.
So they're really gearing up, and they've been well funded in recent years. So they're doing a lot of innovative things. But yeah, a lot of the long-term records are coming from NASA and NOAA satellites.
Okay. NASA's budget is supposed to be cut next year by 3%. Is that going to affect you? And what if people don't want to hear us talking about climate science anymore? Do you worry that NASA budget will go towards new space vehicles and not hiring Gavin again?
I'll skip that last bit. So, the budget process, if you spend any time looking at the federal government in the US, you will realize is a massive sausage making machine, and there's lots of opening gambits, and there's things that happen, and there's things that, so like until you actually have a budget, you don't know what's going to be in your budget.
Okay, and everyone's got their finger in the pie, and everyone has contingencies.
Yeah, I mean, like NASA, NASA is pretty widespread across the country, and and it spends money through universities, through contractors, through the centers that are all over the world, all over the country. This is money that kind of, invigorates the economy and produces great data. So, I mean, I could see that there would be lots of arguments for not cutting NASA's budget. But, the fact of the matter is we're an executive agency, right? We don't exist outside of the federal government. And Congress decides what the appropriation is, and if they said, well, spend less money or spend more money on this, then NASA would do the best that it could with whatever constraints that it's given. Having said that, most of what we do, is stuff that is of use to a huge range of end users, from weather forecasters to disaster preparation to FEMA, USD. I mean, so we produce a lot of data, produce a lot of science that a lot of people use. So, personally, I think it would be a little bit short-sighted to cut that, but we'll see what happens.
Maybe they could just cut the guy that's making conclusions about climate change.
The funny thing is, it's not just one guy, right? And one of the great things about NASA is that it's a totally open data policy, right? So for the most of what we do, the stuff comes down from the satellite, it goes out straight away. So we produce free data. People can analyze it themselves. All of the data, we have a very small operation where we kind of collate weather station, ocean data to produce, statistics for the global mean temperatures every month and every year and things. But it's not a very big part of what we do. But all the code is open source. All the data is public data, so, they could say, don't do that anymore. I say, fine, somebody else will do it. I mean, okay. We've kind of built in that robustness because it's important. It's important that these analyses be transparent. It's important that they be replicable, right? That's a key part of science, because they matter, right? So you can't have a single point of failure. You can't just be, well, if that one guy there goes away, then all this data goes away. No, that would be crazy. And so, we've designed the way that the data processing works such that it isn't just one person. Anybody can actually go and do this themselves. And there are multiple groups who are doing, similar or basically just taking our code and running it. And so, things are more robust than one sometimes fears.
Okay, so if you go missing, I won't have to go look in the shale oil fields. There'll be someone else that replaces you and continues your work, I guess. Continue watching this fascinating conversation for free by clicking on the link below to visit our website, and I'll see you on the inside.
We need to get off coal, right? So you can go a little bit to natural gas, right? But the biggest thing that you can be doing in the US is making a smarter grid, right? So we have huge untapped resources for wind and solar in the US that are unusable because we don't have a connected grid system, right? So North Dakota, Wyoming could be producing huge amounts of wind power, but they're not connected to either the West Coast grid or the East Coast grid.